Okay, so let's try to work a basic LC circuit example. So we're going to start off by drawing the circuit that we're going to work. And telling you what the initial state of the two elements, which is critical no. So the initial state of the capacitor, we'll say, is some V0, initial voltage, and the initial state of the inductor is set by, say, I0, which we'll start out by setting to 0. So then let's try to solve the circuit. So we'll write down just KVL around the loop. So we're saying that V0 is going to equal to the inductor voltage, and that the current, VC, I should say, that's for the initial condition, so let's write that again. VC is equal to the inductor voltage. Now VL is L di dt, and we remember the element relation for the capacitor is IC equals C dV dt. KCL now around the, at this node tells us that IC is equal to minus IL, and if we differentiate that, we see that DIL dt is equal to minus C second derivative of dV dt. Now this is pretty good because this right here plugs in very nicely up here, so we can rewrite that KVL as VC is equal to minus LC d squared VC dt squared. Now this is our second order differential equation. I'm just going to rewrite it, rearranging it slightly. Second derivative of V plus VC over LC is equal to 0. It's a homogeneous equation, and so we'll try a solution of the form A cosine omega t plus phi. And I know it's frustrating if you haven't solved a lot of these equations before, where people come up with these trial solutions. And in this case, I mean, you just sort of notice that there's a second derivative term and the function itself, and cosines and sines have this property that when you take the second derivative you get the function back, so it kind of invites us to try a solution of this form. So indeed, if we take the second derivative, we do get the function back. Of course, we'll get a minus sign, and we'll get the omega out twice, and then we'll get the function. And then we get there for VC, the function, so you'll notice that the A cosine omega t plus phi divides out both sides, and we're left with omega, which we're going to call omega naught throughout here. We're going to left with omega naught equals 1 over square root of LC. Now, technically it's plus or minus 1 over square root of LC, and indeed, if you work this out a little bit more extensively, you can see that that's just fine. Either solution is acceptable. So now if we take this form of the solution, now we solve for one of the variables. Now we have these two other variables, A and phi. So how are we going to figure out what they are? Well, luckily we have two boundary conditions for this problem. So the first boundary condition comes from the voltage on the capacitor at time 0, which is V0, and that's going to be A cosine phi. The second boundary condition is a little trickier to see because it's not actually a boundary condition in the voltage, it's a boundary condition in the current. that IL, which you remember is minus IC, equals 0, but that's going to be equal to minus C dV dt. So that tells us that dV dt is 0. So if we take the derivative, we get minus omega naught A sine phi equals 0, substituted in for time equals 0 already. And we take the, we look at this and we say, well, it means that either A is 0 or phi is 0. That's the only way we can get, we know omega naught is not 0, so the only way we can get that equal to 0 is that if sine is 0. But if A were 0, there's no way we could satisfy this boundary condition, because then V naught would have to be 0, but it's not. It's given to us, so we can't assume that it's 0. So that means that phi has to be 0. Okay, so that's cool. So now if we know phi is 0, we can substitute into the earlier boundary condition, and we say cosine 0 is 1, so we get that A is equal to V naught, and now we've solved for Vc. So in this case of the homogeneous form of the LC circuit, we find that it's equal to it's equal to V naught cosine omega naught t, and phi is 0. So that's the answer for Vc. Let's plot it. It starts out at V naught and it oscillates. It has a frequency omega naught, which has units of radians per second. That relates to traditional frequencies in hertz by a multiplication of 2 pi f cycles per second. That's because you have 2 pi radians in a cycle. And just for completeness, remind yourself that the period is 1 over the frequency for an oscillation, which is going to be 2 pi over this omega naught. So that tells us that if we go peak to peak here, we get 2 pi over omega naught. Now, in this case, the period is the period is defined there. So the next step is to figure out what the current is. The current, well, you remember the element relation for a capacitor. If you don't remember it, you should have this by heart, completely by heart. I equals C dV dt. So that's equal to C times, let's take that derivative, minus a omega naught sine, that's a V sine omega t. And there you have it. We can plot this on the same curve. It's a minus sign, so it's going to be going like this. Now I always try to remember that in a capacitor, you always have to have current before you can get a voltage, because you need current to flow into it before a charge can accumulate on it. So current comes pi over 2 in front of the voltage. Now I drew them the same magnitude, but they're not. The amplitude of VC over the amplitude of IC is equal to V naught over C omega naught, V naught. So conveniently the V naughts cancel, and we end up with a 1 over C omega naught, which is square root of LC over C, which is the square root of L over C, which is something called ZC. It's called the characteristic impedance. So just like the resistance is the ratio of the current to the voltage in a resistor, the characteristic impedance is the ratio of the current to the voltage in an LC circuit in one of the elements. Now, what is actually going on here that's causing this oscillation to occur? The way to think of it is in terms of energy. So initially in this circuit, right at time 0, we have energy 1/2 CV naught squared. At time equal to, well, the period over 4, you have energy equal to 1/2 L IL max squared. Now that maximum IL you can get from this here, so that's C V naught omega naught squared. We can do a little bit of rearranging here using this characteristic impedance and canceling things out, and what we're going to find is, well, that LC will cancel with the omega naught. We'll end up with the V naught C, so we're going to end up with 1/2 CV naught squared again. So that's quite remarkable. It's the same amount of energy that gets transferred into the capacitor. And then in a moment later in time, well, here we've gone from 0 to t over 4, now we're back to t over 2. Look, the capacitor has 1/2 C, and now we're just at minus V naught squared. And so that's, when you square that, you get the same thing, 1/2 C V naught squared. So the energy oscillates at 2 omega naught. That's really surprising, okay? But that's the way it is, because it doesn't care if it's a minus voltage or a positive voltage. So the amplitude oscillates at V naught, at omega naught, the energy oscillates at 2 omega naught.